Hi, I am Haruna Umar Adoga from the School of Computing Science, University of Glasgow, and today I want to present our work by myself and my supervisors, Yahya El Khatib and Dimitrios Pezaros. The title is on the performance benefits of heterogeneous virtual network functions execution frameworks. So, a brief introduction to network function virtualization. This allows service providers to make use of softwareized network functions rather than hardware network devices. So, these network functions could be functionalities such as network address translation, deep packet inspection, or load balancers. In terms of the components that are required for this to be implemented, we have the Etsy NFV architectural framework that's shown on the figure here on the right. So the first component we have is NFV infrastructure itself. Then we have the virtual network function. So this could be NAT DPI or load balancer. Then we have the NFV management and orchestration component, which is the Mano component that is responsible for orchestrating network functions. So, in terms of deployment of virtual network functions, so far this has been carried out using VNFs, using virtual machines, lightweight containers such as Docker, unikernels, or kernel-based packet processing elements. DPDK is also another option for deploying virtual network functions. The separation of user space, that's the control plane and data plane brought by SDN, gives another option in terms of implementing virtual network functions. So virtual network functions could be deployed using the data plane of switches. So we could use an SDN aware data plane, or we could use this the idea of network programmability, where we have the programmable data plane as an option of deploying data plane of deploying virtual network functions. In terms of the contributions of our work, we have a detailed breakdown of this in the paper itself, but a summary here is that we started by asking two questions. Basically, we asked what network functions could be pushed down to the data plane of the network. The second question we asked is in terms of the performance benefits that we could get from using this diverse virtual network function processing elements. So, in terms of contribution, we have motivated the need for deploying virtual network functions at the data plane. Also, we presented a classification of virtual network functions, a representative classification of virtual network functions that are commonly used by service providers, as well as a performance evaluation of diverse execution frameworks. We also provided some recommendations for implementing virtual network functions based on the results we have obtained from our experiments. In terms of the representative categories of that's VNF, we have IO bound category and the compute bound VNFs category. So these two major categories. In terms of the IO bound categories, we have functionalities such as the ACL firewall. We have header classifier or caching, for instance. So they basically carry out functionalities such as IP header lookup or data store access. As you can see from this figure, this NF could access data from external storage to check, for example, maybe if it's caching or some sort of database for match action, key value store in terms of firewall authentication rules. So this behavior is basically done by IO bound VNFs. We have the other category, which is for compute bound VNFs, where more fine grained operations are carried out on packets, where we have things like compression, QoS, encapsulation, regex matching, as well as encryption. So the table here, you can see from the table one here, this like a list of the functionalities we have that's on the edge, compute, and IO bound virtual network functions. To evaluate the performance of virtual network functions, we designed two test beds actually. So the first test bed is what you're seeing on the right here, where we have the packet generator device that's been configured with the PKT gen. So we have packets that have been generated here destined for the VM that's on the device under test. So that's VM2. VM2 here is hosting the FTP and HTTP services. So virtual switch has been configured on Linux kernel that's 5.4.059 generic. That's on Ubuntu 2004, and we have the device on the test with Intel Core i7 8700 at 3.20 gigahertz with 6 CPU cores actually, and virtual interfaces were configured to 1 GB speed. So we have match action rules. As you can see from this figure, match action rules are installed on the dataplane switch here, as well as rules on the VM here. That's the user space NF. So traffic destined for VM2 are actually made to go through either the user space functionality or the data plane at any given point in time. In terms of performance, we started by evaluating the data plane firewall bandwidth, which for 64 bytes packet was able to process up to 226 megabits per second. So this evaluation basically was carried out for 64 bytes up to 1500 bytes packets, which is the MTU size packets. For the data plane firewall as well, for 1500 bytes packets, we're able to obtain 957 Mbps, which is about 96% of the line rate. Line rate here is 1000 Mbps. The data plane router NF was able to process up to 1185 Mbps for 64 bytes packets as well, as you can see from the figure on the right, and 905 megabits per second for 1500 bytes. User space firewall peaked at 150 Mbps. That's also for 64 bytes packets, which is basically a decrease from what we obtained using the data plane firewall implementation. So the user space router bandwidth peaked at 800 megabits per second. So in terms of CPU utilization, we were able to get up to around 2% of CPU utilization. That's for the data plane firewall. For the overall cost, that is. Then the data plane router used up to 8% of overall CPU cost. User space firewall used up to 10%. The highest was the user space router, which used up to 14% of the overall CPU cost. The second testbed we designed made use of DPDK and containerized NFs. So OpenNet VM, which is a framework for building lightweight containerized network functions using DPDK as well. So we made use of that. We built our NFs on OpenNet VM. So we have network functions that are implemented on the device on the test. In terms of device specification, we made use of the same um, commodity server that we used in the previous slides. That's the first test bed for consistency. Each uh, VNF was tied to a separate CPU core for performance isolation. So containerized VNFs as well were tied to separate cores. So in terms of performance, you can see from the figure here on the right, where we initialized 16,000 packets to start with, to send packets. That's from the packet generator through the network functions to the host. So we measured that. And the duplicate firewall NF processed around 2 million packets per second for 64 bytes packets. You can see that from this the figure on the right here. So DPDK router NF processed about 1.8 million packets per second at 64 bytes as well. And you can see what we obtained for 1,500 bytes packets. So the containerized firewall bandwidth peaked at around 660,800 packets per second. So that's for 64 bytes, as well as containerized router NF, which was able to process 360,800 packets per second for 64 bytes as well. So to summarize our work, the work we've presented in this paper, in summary, we started by motivating the deployment of SD and aware dataplane VNFs. So we did this by presenting what has been done so far and the sort of status quo in terms of implementing virtual network functions, and motivating the need for considering the data plane as a suitable option for deploying data plane for deploying virtual network functions. We evaluated the performance of some network functions that are widely used, the firewall and router as well, using diverse processing packet processing elements. Then we made use of multiple commodity servers as well to avoid resource contention problem. So tying each VNF to a dedicated CPU core also improves its performance as well. And a high number of CPU cores are required for kernel bypass VNF implementations such as DPDK, because each VNF runs on a specified CPU core. So in terms of what NFs should be deployed where, we have some operations such as floating point compression or and decompression, which would benefit immensely from user space deployments. So since we have not considered all data plane implementations, so we cannot claim that our results are generalizable for all data plane implementations out there. This is based on the environments we've evaluated, and we have detailed that in the paper. In terms of future directions, we hope to evaluate this on programmable hardware switch as well, which gives more options for offloading packet processing onto programmable data plane. Then consider emerging use cases such as e-healthcare, mixed reality, autonomous vehicles, which would give a hybrid scenario whereby we have some functionalities deployed on user space hosts while others deployed on data plane hosts based on the types of functionalities and complexities of functionalities, since we have diverse functionalities and different types of service requests out there. So this involves the creation of a service function chain that would have a hybrid sort of network functions processing elements. I would like to thank you for listening, and please to leave comments or questions or feedback And you can either drop comments here or send me an email anytime. Thank you.